Hey there everybody, Mr. Dickin here. In this video we're going to continue our discussion on transformations of our parent functions. That's when we had quadratics and absolute values and cubics, all of that. But now we're going to throw in two more types of transformations. So we've already discussed how we would shift things, that's called a translation. Now we're going to do reflections and stretches/shrinks. So reflections is just like a mirror. It reverses things. So you'll see something backwards or upside down, depending on the type of reflection. A stretch or a shrink means a graph becomes either taller by a certain scale factor or shorter by a certain scale factor. So let's get into a warm-up first, just to get our brains going. And so this will help us kind of recall what some of those parent functions were. All right, so if I look at number one here, I want to sketch a graph of this function. I'm noticing first and foremost it's an absolute value function. So graphically speaking, it's going to look like a V. Easy way to remember that, absolute value starts with a V. And then I'm looking at, okay, I've got a -2 inside and a +3 on the outside. So minus inside means it's going to go to the right, and a plus on the outside means it's going to go up. So I'm going to have this shape here, a V, that went to the right 2 and up 3. Well, let's see if that's the case. Hot dang it is. So normally it starts off at 0, 0. We went to the right 2, we went up 3, and shabam, there we go. All right, next one. We've got a square root function. So remember, square root functions have a set endpoint, and then they kind of look like the top half of a tipped over parabola. On this one, I'm not seeing any numbers added or subtracted inside with the x. However, I am noticing a -4 on the outside, so that tells me we should be going down 4 units. So let's take a look at our graph. Lo and behold, that is the case. It started normally at 0, 0, shifted or translated down 4, and then for the extra points, we followed that 1, 3, 5 pattern. Well, we ran out of graph, but it would be over here. All right, let's see two more, and then we'll get into the new stuff. Let's see, number 3, we've got a cubic function with a +3 and a -2. So that tells me a plus on the inside, it's going left, and a minus on the outside, it's going down. So left 3, down 2. There you have it. We started 0, 0, left 3, down 2, and there we are. And lastly, we have a -4 and a +1. This is a squared function, so it's going to be a quadratic. And we went -4, so to the right, and then +1, that's going to go up. Here's our graph. Again, this vertex normally starts at 0, 0, went to the right 4, up 1. And then additional points, use that 1, 3, 5 pattern, so up 1 over 1, up 3 over 1. If we had more graph, up 5 over 1. All right, new stuff. So now we're going to talk about reflections. We can ignore this link to Desmos piece for right now. That'll be posted later on. So reflections happen anytime negatives get thrown into the mix. All right? So what I mean by that is if you have a negative sign either in front of the function or inside the function directly on the x, you're going to have some sort of a reflection. Now, if it reflects about the x-axis, that means it's going to get flipped upside down. So if it gets flipped over the x-axis, it's going to get upside down. It's going to be flipped upside down. So what that means is if we normally had an absolute value function, for example, so an absolute value function looks like a V. If I threw a negative in front of that, it would be an upside down V. So negatives out front flip things upside down. A negative on the inside flip things across the y-axis. So that's going to be a horizontal flip. Now what I want you to think about here is the types of functions we've been dealing with is if I gave you a parabola, you're not going to know if that got flipped horizontally or not because it's symmetric, right? It had that axis of symmetry. the left side is the exact same as the right side. That's going to hold true for absolute values as well. We're not going to know if it got flipped horizontally. The only time that's really going to come into play is if you have a square root function, right? Because it's very easy to tell, in this case, the red versus blue, because one has been reflected, the other one has not. And then the other graph that will be kind of telling is going to be our cubics. But cubics are kind of peculiar because you could argue with these cubics, it's either upside down or horizontal. You could argue either way and still be correct. And the reason for that is negative x to the third versus negative x to the third. Well, those are identical statements. So, a negative on the outside is going to be the most frequent one. A negative directly inside, we do have to keep track of. And if there's other stuff going on inside the function with the x, we're just going to have to factor that negative out. And we might see an example of that down the road. All right, so let's get into vertical stretches and compressions. Now, first, before you read this and have a mild panic attack, because I agree it is kind of daunting, what I want you to do is really focus your attention just on this part right here, okay? This value of c is just some coefficient, okay? So it's going to be some number in front of one of our functions. And our functions, we had quadratics, we had square roots, absolute values, yada, yada, yada. So the numbers that they're referring to would be coefficients in front of those. So I'm just making up a bunch right here. All this stuff is saying is that if you have a coefficient or a number that is bigger than 1, so if your coefficient is bigger than 1, you're going to be stretched. So your graph is going to be taller. So right here, 2x squared, that's going to be 2 times as tall as a normal x squared graph. Over here, 7 is clearly bigger than 1. So this graph would be 7 times taller, or it would be stretched by a factor of 7 as compared to a typical graph. Then it says if our coefficient is between 0 and 1, so by being greater than 0, this part right here, really that's just saying, hey, it's going to be positive. Because we know if there was a negative, it would just be a flip. And then by saying it's going to be less than 1, well, that just means it's going to be some sort of a fraction value. 1/2, 2/3, 5/7. So it's going to be some sort of a fraction. I guess you could argue that, maybe it'll be a decimal like 0.5, 0.25, whatever. And what that means is our graph is going to be compressed or shrunk. So for example, this 1/2 square root of x, that's going to be 1/2 as tall, or shrunk down by a scale factor of 1/2, as its normal graph. So here we've got some examples. The original graph is going to be blue. The new graph will be red. So here, if I took an original graph, you guys will learn down the road, this is going to be a sine function or periodic function. If I look at this blue function, that's my original. And then if I look at the reddish, maroonish, purplish, whateverish color, that's the graph that's been stretched. And I know that it's been stretched because it's clearly taller, right? The humps are a lot higher, the dips are a lot lower. So it's been stretched by some factor, some c value, some constant value, and that had to have been bigger than 1. Similarly, if I look over here at my second graph, we have our original blue, so the blue is the original, and then this reddish, maroonish, purple, whatever, that's going to be our shrunken down version of the graph. And that's because we have some coefficient that is less than 1. In this case, if I were to guess, I'd probably say it's probably 1/2, maybe 2/3, right? This reddish graph looks like it's maybe half as high as the blue one. Who knows? All right. Now let's get into the process for graphing these. So whenever you're graphing a function, you always want to follow a specific order. First, if there's any reflections, be mindful of those first. So if you're getting flipped upside down, take care of that first. Then figure out, are you being stretched or shrunk at all? Once you figure that out, go on to translation. So is it shifting up or down or left or right? Steps 2 and 3, you can probably do interchangeably of one another, but we do have to make sure that reflections get taken care of first. So always reflect first. All right. So here we have some examples. We want to figure out the transformations that are taking place. Now when I do this, I'm keying in on any number that is being thrown into my function. Just by looking at this first function, I can already tell you it's going to be a parabola because I'm seeing this x squared. This 2 out front, that's being multiplied. So that's going to be either a stretch or a compression. Well, 2 is bigger than 1, so it's going to be a stretch. So this x squared is going to be stretched by a factor of 2. I've got a minus 3 inside my function. If I think back to previous videos, that means it's going to go to the right 3 units. And then a plus 5 on the outside, it's going to go up 5 units. So stretch by a factor of 2, to the right 3, and up 5. Next one, we have another x squared, so another parabola. One thing that we do have to be mindful of, though, is I'm seeing a negative on the x. Okay, so that tells me it's going to be reflected over the y-axis, so a horizontal reflection. But if you recall, we have to be careful if there's other stuff going on in the parentheses. So what I'm going to do is, just so I can maintain a plain old x, is I'm going to factor out a GCF of a negative 1 inside the parentheses there. So really all that does, is it just kind of changes the sign of that second value. And the whole purpose is I want this x, I want it to be just a plain old x. I don't want coefficients on it if I can avoid it. All right, so now let's see how that changes the graph. Well, clearly there's going to be a reflection. Then I've got the minus 1. And then I've got a minus 2. Well, the minus 1 and the minus 2, those are just going to control left and right, and then up and down. A minus 1, that's going to go right on the inside. And then a minus 2 on the outside, that's going to go down. So here we have reflect over the y-axis. So that's a horizontal reflection. And then right 1, down 2. These ones are always going to be the most troublesome. Anytime you have to take out a negative, just please be careful. That being said, on the next one, you'll notice we have another negative. Now, some of you are not going to like this explanation. This one does not require a factorization because this negative sign, if I think of order of operations, is technically a coefficient onto this x squared. So if I really wanted to, there's technically parentheses around that x. Obviously, it looks silly to put parentheses around plain old x, but you could. Now, order of operations says that we have to deal with exponents before multiplication, so there's no factoring needed for this particular example. A dead giveaway is if they include parentheses, you're probably going to have to factor it out. If there's no parentheses provided, probably don't have to worry about it. All right, so we have a few different things going on. We have a negative out front. That's going to be a flip upside down. So if I think of this graph, it's a quadratic, but it got flipped upside down. So it's going to look like that. And then I've got a plus, my bad, plus 4. So that tells me it's going to go up 4 units. All right, last one. Yet again, we've got a factoring that has to take place because we have negatives directly on the x, and that's contained within parentheses. So I'm going to take out that negative. And when I do that, I'm left with x plus 4. So basically, it's just a GCF negative 1 that I took out. Nope, and then we have plus 6. All right, so now let's look at what we have. We have a flip It's going to be a horizontal flip, so a left-right flip over or across the y-axis. We're going to go to the left 4. We're going to go up 6 units. Booyah. All right. Now let's get into some graphage. All right, we've got 4 to graph. About 15 minutes deep. I'll try to keep this around 20 to 25 minutes, but no promises. We should be able to get it done, though. All right. Let's see, this first graph, we're going to have a quadratic. This quadratic is going to be stretched by a factor of 2. What that means is instead of following that 1, 3, 5 pattern that we've come to know and love, we're just going to double that. So now it's going to be the 2, 6, 10 pattern. And that's just to get our extra points. And then we have a -2 on the inside, so that tells me it's going to go to the right 2 units. All right. Let's see, normally we'd start off at 0, 0, but we got shifted to the right 2 units, so my vertex is going to go right here. And then there's no flips to keep track of, so now I'm just going to follow this 2, 6, 10 pattern. What I mean by that is I'm going to go up 2 over 1, up 6 over 1, and then if I had more graph, I could go up 10 over 1. So up 2 over 1, and then from that point, up 6 over 1. I can use the fact that this is symmetric to get some points on the other side, so on the left-hand side. And now to the best of my ability, we're going to get a parabola going. There we go. That is our graph in all of its splendor. All right, next one. 1/4 x cubed plus 2. Okay, x cubed, a cubic function. Normally looks like one of those. If I think about the table of values that we made for those, we had -2, -1, 0, 1, and 2. And those created y values of -8, -1, 0, 1, and 8. Well, if I'm taking those and multiplying them by 1/4, that's really going to be, let's see, instead of -8, what's 1/4 of -8? That would be -2. 1/4 of -1, that's going to be a fraction. I don't feel like graphing fractions, so I'm going to ignore that. 0 is going to be 0, 1 will be another fraction, and then 8 would be a +2. Okay. So now the whole reason I'm doing that is so I give myself kind of like a framework for when it comes to plotting points. All of these points are going to get shifted up 2 units. So normally, if I started my graph off at 0, 0, right, I'm going to take that and now shift it up 2 units. So right here is going to be where my inflection point is going to be. And then, according to my little table here, at -1 and +1, I'm not going to bother trying to graph points because we got fractions there. So I'm going to do -2, -2, but remember it had to get shifted. So -2, -2. Normally it would have been here, but remember we're moving everything up 2. So normally it would have been here, but it's getting shifted. So now it's going to be right there. And then we had 2, +2. So 2, +2. So originally it would have been right here, but it got shifted up 2 units, so now it's going to be up there. Now to an untrained eye, this kind of looks like it would be a linear function, right? You could just do and call it a day. However, we know, since we are wicked smart math folks, that it's actually a cubic. So we know the general shape of this thing is going to look something like that. All right. Onward we go. Oh boy, we got a flip. Nice. All right. So here we have a reflection, a translation to the left and up. So let's see. I have an absolute value function. Okay, so it's an absolute value, but it got flipped. So this is going to be the graph format that I use. It's going to be an upside down V shape. And remember, these points, you just go down 1 over 1, down 1 over 1, down 1 over 1. And instead of starting off at 0, 0, we went to the left 4 and up 3. So from here, let's go left 1, 2, 3, 4, up 1, 2, 3. So right here is going to be my vertex. Aye. All right, and once we have that, we just kind of fill in the rest of our shape. Down 1 over 1, down 1 over 1, down 1 over 1. You'll notice I'm going down, again, because this was flipped. And we're done with that. All right, last and final one. Let's see, we have a handful of things going on. We have a stretch factor. That's not a highlighter. We have a stretch factor of 2. We've got a reflection, and we're going up 4. And this is all a square root function. So this thing normally looks like that. But according to this guy, it got flipped around, and it's going to be across the y-axis. So it's a horizontal flip. So it's no longer going to look like that going to the right. It's now going to go to the left. And it's going to get stretched by a factor of 2. And then we're going to move everything up 4. So let's kind of take this piece by piece. All right, so we'll handle the reflection first. Normally we'd go up 1 over 1, then up 1 over 3, up 1 over 5. So these follow that nice quadratic pattern. So we've handled the reflection, but they got stretched by a factor of 2. Well, that means each one of these, they're going to be twice as tall as what they normally would have been. 2 ways to think of that. You could either picture, okay, I'm just going to double the y value. So this has a y value of 1, I'll make it a 2. This has a y value of a 2, I'll make it a 4. Or instead of thinking of it as up 1 over 1, up 1 over 3, up 1 over 5, you can think of it as up 2 over 1, up 2 over 3, up 2 over 5. Doesn't really matter. So if I do that, these are going to be the resulting points. Okay, so now that is taken into account both the stretch and the reflection. And now all that's left is I just have to move these things up 4 units. So each point will get moved up 4. Oop, can't do that. Okay. So if I move this first point up over 4, there we go. Up 4, up 4, and up 4. So that is going to be the resulting function. Woof. Okay. Real quick, I'll just put all of the functions that we had up there. And let me see if I can clean up the first one with a highlighter, maybe to make it a little bit more. Yeah, that really didn't do anything. Whatever. All right, so that's basically the gist of what we're doing with regard to functions. All right, so we're going to spend another few lessons just kind of putting all this stuff together. The behavior is going to be the same regardless of what function shape. Doesn't matter if it's a parabola, a cubic, an absolute value, square root. All the flips, stretches, translations, shifts, everything is the same, no matter the type of function. All right, that's all I've got for you. You know the drill, folks. If you have a question, please let me know. Shoot me an email or holler at me during a Zoom or something. And as always, good luck, have fun, be safe, roll tide.